for this one, we have a sensor that acts like low-pass filter with a gain of 10 and a time constant of 4 seconds. And we have to sketch the unit step response of this sensor showing units on our axis. And we should be able to do this with explicitly solving a differential equation or inverse Laplace transform. So if we're to draw our transfer functions, we'll have gain on the top. On the bottom, we have the standard form of s plus as plus b, but our a is our time constant. It's going to 4s, and then 4s, and then we'll have 1 here, and that's the standard format for our transfer function. And if we were to draw our step response, so for step response we have t, the time, on our axis, and we have just magnitude on our y-axis, and start at 0, so it's gonna reach a steady state, and we know that at 1 time constant, so 4 seconds, we will reach 0.63% of the steady state output. So 63% of the steady state output, and about a 4th time constant, which is going to be 16, will reach about 9.8 or 0.9, 0.98 of our, so 98% of our steady state output. But since we have a gain of 10, we know our steady state output value is going to be 10. So I'm going to change it to 9.8 at 4 time constant. So at 16 seconds, it's going to have 9.8 of magnitude. And here we'll have 6.3 of magnitude at 1 time constant. So this is the case for our first order. But what if the filter has second order? This is first order, because our bottom only has 1s. For our second order, so we'll have something like same thing. Then we might have a little different. So in general, the picture is going to look like where this is our steady state value, and same time constant reaching as 6.3, and this is we'll have about 6% overshoot, and so on. And also reaches, yeah. So that's what second order would look like.